Good morning, everybody. I think we are ready to start. It's Jan Graves from Intel, and I'm Vladimir Ivanov, and we would like to give an update on Vector API project, which has been working on. We have been working on as part of Project Panama. So, since we have a joint talk, as a bonus to this slide, you have one more. And let's start. So,
okay.
Yeah.
So the Vector API is, it's motivated by, we want to vectorize things. We want to do things single instruction, multiple data. So given a loop body like this, we want to get it to fully leverage SIMD registers. And in that case, we want it to look something like this, where we can represent packed adds, packed operations in an idiomatic Java way. So our goals, just up front before we dive into this, we want a maximally expressive API. So something you can do pretty much everything with is the ultimate goal, with coverage of all the operations that one can reasonably expect on a particular architecture. As far as performance is concerned, predictable performance, good code quality, and is competitive with auto-vectorization. So if you're doing it yourself, and we give you the tools to do it yourself, we want you to be able to at least match auto-vectorization, but that's a reasonable bar to shoot for. We want you to be able, as a goal, we want you to get well above what you can get with auto-vectorization, because if you're doing it yourself, you're putting the effort in, you should see some results. And then we want some ways to make the code portable. So fallback for narrower vector support on different architectures or wider support. So ways to write code that can transition across different vector sizes and without you having to express a kernel multiple different ways. So this was last year. John had proposed the strawman vector API, an immutable vector type with functions like you see here, 2 parameters, element and size. We call it the shape, size, it's essentially a bit width. And we've worked on, we had a prototype implementation, I think, of int vectors based around these machine code snippets, which Vladimir is going to jump into here in a little bit, and raw vector types called superlongs. So fast forward a little bit. We had a draft API implemented off of the original spec, and the goal is to get code written here to our desired code shape. So the vector API operations are specified in an interface, but live in, I want to say, a single-tenant 0 vector instance. Primarily this is because it's difficult to parameterize, at least in generic form, the shape and the element size when it comes to rendering and marshalling vectors to and from data sources. So what you do is you query the system for a vector instance of a particular shape and size, and if such a thing is supported on your native architecture, then it gives you the 0 vector for that element type and shape. And then from there, you can instantiate other vectors, etc. And then you also have a 0 value, which is usually pretty useful for a lot of different operations. So what we still are sort of holding off on or working on is that in the current shape, we don't have full type specialization. We're still talking about parameters in their box form. So we have to kind of dance around the boxing issue a little bit. Under the hood, a vector parameterized by integer or floats will be behaving in a performant way if you stay inside vector code. If you're writing a bunch of code with the vector objects chained together, there's not really boxing occurring. It's just a parameterized inputs and outputs of scalar types and data types that is concerned with the integer parameter. If you're projecting scalar values to and from, there's some auto-boxing effects. That's not a deal breaker. In a couple slides, we've actually refactored this in a way that this really is no longer too much of an issue. Let's see here. basically what we're getting at is full value types. You know, we've seen a lot of talk so far about minimal value types, but to fully realize the vector API, full value types with enhanced generics and jetpacks and flying cars are still, you know, something that would help us fully realize the vector API. Another important coding component is being size agnostic with your code. So you can ask for a particular vector instance of an element type and a width, and if you don't have that available on your local architecture, then you're kind of hosed. So if you're expressing your kernels, you want them to be as you want to loosen the type constraints on code wherever you can. So given some vector of a particular element, you don't really care about its size, but you can query the length of the vector if you're striding through arrays or byte buffers or whatnot. So we want to be able to express code in this way. So given this vector loop, we can have a vector loop that looks something like this when it's vectorized. So if you see here, let's see, do we have a, yeah, not so much. So around the loop kernel with vector at integer s, we've loosened the constraints up, and the 0 vector is threaded through this method. So essentially this prevents you from having to write a kernel for integers of 128 bits, integers of 256 bits, integers of 512 bits, et cetera. You start by just saying, give me the vector spec that will fill the hole in my vector kernel. So a really important use case for something like this is the aligning your loop kernels. So a really common thing to do is to work your way up to alignment to your main vector loop, and then do a fix-up loop at the end. So you have a pre-loop, a main loop, and a post-loop. And so being size agnostic lets you write things like this once, or even factor these out so you don't have to write 3 loops if you have a more higher order-ish approach. So being size agnostic prevents blow up in your code from having to support lots of different vectors. So where we're at now with the API structure is we have a top-level vector parameterized by shape and element type, and then we have subclasses, abstract classes implementing or fixing the element type, like int vector and float vector, and then underneath that there are concrete vectors where the operation basically reside. So this fixes the issue of scalar gets and puts in our vector operations, and it lets us talk about things in terms of primitives and not box primitives, and like put a lot of pressure on auto boxing. So in Project Panama, this is essentially what it looks like now. We have a vector interface at the top level, and then we start to specialize partway with an int vector here with a shape that is still yet to be determined, and then when we drill down to the very bottom, we start getting vector classes that are specific to elements and shapes. And then within those, we have particular bindings to, in this example, it's something akin to code snippets. But we would be specifying either at the C2 side or an intrinsification side where what operation corresponds to this specific vector of this specific type and size. So we get semantics and size and all that down at the bottom layer. And so initially we implemented a lot of this with raw vectors and the super long types, and this is the original work from last year, and we're now starting to transition into something like we just showed you here, which is more specialized, and I think this is where I hand off the baton to Vladimir to go more in depth to this.
Thanks, Jan. So raw vectors are used to hold vector values. They are erased, no information about the size of elements and types, and we encapsulate them inside typed vectors. So right now in Panama, we have a typed vector and raw vector separation to simplify the implementation. When we started playing with it, we faced a bunch of challenges, and the most important one was optimizing away vector boxes. Since all the classes we create, they are inherently identityful, we need to do a significant amount of work to eliminate them. And it doesn't work in all cases. So other two, Jan mentioned that, primitive specialization and vectorizing higher order operations, but for now I want to focus on optimizing away vector boxes because that's the crucial step in order to get predictable vectorization of your code. So we are living not ideal world right now, and there is a mismatch between JVM and hardware VM is ran on. So we don't have any primitive types larger than 64-bit, so we can't natively describe value-like values larger than that. So we can try to rely on escape analysis in JIT compilers, and sometimes it works. So for example, in this particular case, I use a bit simplified API, so it has typed vectors explicitly available and used. So I won't use the vector interface directly. So the point here is to demonstrate what kind of challenges C2 or other JIT compiler faces when trying to get rid of vector boxes and scalarize vector values. So in this case, we have a vector local in the basic block in the loop body, and C2 does its job fine. No boxing, so all the vectors are in registers, so the code, the machine code is quite nice. When it becomes a bit more complicated, like a reduction of our array, it becomes much harder for C2 to keep up, and it fails to eliminate the boxes. So there is you could think that there are two states, escaping, non-escaping, but there are more states, like there is non-escaping and scalarizable. So even if the object is non-escaping, it doesn't necessarily, the JIT compiler doesn't necessarily can scalarize it. So in this particular case, C2 detects that the value is not, the object is non-escaping, but it can't prove it can scalarize it, because C2 implementation is control flow insensitive, and it just gives up when it sees merges of objects in the IR. So you could think that, okay, let's use a different compiler which had a fancier escape analysis. What's the problem? The problem is more of that the escape analysis is not the right tool to get reliable box elimination. So for example, if some JIT compiler heuristics, inlining heuristics doesn't decide to inline a call, we have to box a value into a box to pass it inside a callee, inside a method, or receive a value. So JIT compiles do local analysis, and the escape analysis should be global to get good results. Users can help JIT compiler by, for example, writing vectors into heap, and it defeats escape analysis as well. Identity-sensitive operations also are possible, and it's hard to educate users to avoid that, especially if you use some helper code like libraries, and such code can be somewhere down the call stack. So if users can experience problems even if they don't write that code directly, but use some libraries to work with. For example, you have some collection, and and it tries to compute identity-sensitive code, identity hash code, for example. So, yeah, escape analysis C2 is brittle due to numerous limitations in the implementation and in the approach in a whole. But, well, we have been working on value types like for 3 years, and well, they're perfect fit for vectors. Let's wait for value types and get rid of any problems with boxing. Unfortunately, full-blown value types are not there yet, but hey, we have minimal value types, and we are the third talk where we will cover some of the aspects of minimal value types. Here we will try to describe the experience working with value types, building something on top of it. So I won't cover what are minimal types, what are the minimal types. So it's a first version, that's it. It's deliberately kept minimal to get something done quickly. And if we want to get a value type, we have to create a value-capable class. And at runtime, we get VM derive a value type for us. So at runtime, there are two classes. On bytecode level, there are objects and values. So there are L types and Q types. And Q types are represented as derived value class. So the key in the name is minimal. So what kind of limitations does it impose on us? Oops.
There we go.
Sorry about that. So what kind of limitation does it impose on us? So no subclassing. So the hierarchy, we have the separation between typed and raw types doesn't work anymore. So we have to flatten it. So we have to come up with a typed vector and which implements an interface. So embedding value types into another value type doesn't work as well. So we can't encapsulate the raw bits of a value in a value class and keep it flattened. So we have to do it ourselves. So we end up with the following, in the following state where we have typed vectors, which VM should be able to map to vector register. Before that, we worked with raw types, so single type per size, per shape. Another thing is that there is no way to directly invoke a method on a value. So it has to be boxed first. And if we want to invoke a method on a vector and avoid boxing, even intermediate box, short-lived, we have to avoid invoking methods as instance method on values, on vectors. So it forces us to provide a method handle-based shape of vector API. So all vector operations are exposed at method handles because MVT supports only value type operations on value types as method handles. Wrapping value types into objects doesn't work. So so how does it look like? So let's look at the memory layout. So we have multiple choices, and in Panama, we are stick with the second one. We just put a payload as long fields, and that's it. But there are more choices. We can put each field for every element in the vector, or just reserve a space, and that's it. Don't expose any fields. What kind of pros and cons different approaches have? So what if we don't have any fields on value types? So we have to provide special factories and extractors to get a user's hand on the actual content of the vector, because vvis field and get field won't work because there are no fields declared. So we have to cover that for ourselves. So what if we try to piggyback on what the minimal value types provide and just declare the fields as elements as fields? So, well, it should work, right? So if you want to access an element, just use get field and name the corresponding field, or to compose a vector, just use a vvis field and get as a result a vector with updated element. Well, It looks like it fits pretty well until we realize that in order to avoid any boxing, we have to intrinsify those operations. Because we have vectors in registers, and if we try to access anything by offset, we have to spill the value into memory, update it, and then load. Well, that doesn't look that attractive. So we want to use special instructions provided by the instruction set architecture, and we have to intrinsify. It means that we have to intrinsify implementation of those bytecodes. Moreover, what about endianness? So how to order the fields? So depending on the architecture, the fields can be in a different order. Well, more problems with fields. So what about flattened arrays? So unlike other use cases for minimal value types, flattened vector arrays aren't that important. So the benefits are that we get array accessors for free by MVT, but the downside is that users have to create their own arrays. And comparing to primitive arrays, which are ubiquitous in the Java world right now, they're used everywhere, it's much better. We don't have any benefits in layout perspective. So in memory, data is flattened. So whatever we use from memory layout, it doesn't matter much. So from usability perspective, it's much better to work with primitive arrays than with explicit flattened vector arrays. But as a downside, we have to provide special accessors to be able to extract a vector from a primitive array and write it back. Another benefit of current implementation of MVT is vector calling. We can easily get vector calling convention by slightly extending what is done for value types. So right now, C2 supports special calling conventions where values passed as fields in registers. We can extend that for vectors and pass vectors in registers. So avoiding any boxing when passing vectors inside some helper function, callee, or getting it back, which should significantly reduce the need in boxing. So let's look at the examples. So a simple one, vectorized dead. We have a loop over an array and loading vectors from two arrays, summing, and writing the result in the third array. So let's focus on the loop body and see how it goes. So the first question, how to get access to the actual operations. So operations on vectors are encapsulated in method handles, and there is a need to do CPU dispatching, some way to detect what's available on the current machine we are running on. So we can implement that using factories. So for example, query that at runtime, what's the maximum size of the vector available, and after we get one, getting the most optimal implementation of the operation on the vector shape we need. So here we want a vectorized add on two vectors of, well, maximum size. So okay, we have all the operations needed as method handles to implement that. So what kind of options do we have? Let's try to invoke them, right? We need to load, two loads, sum, and then store. Will it work? Not really. We have value-capable classes mentioned on the bytecode level at the call side, but the method handle is typed as a derived value type. So there is a mismatch. There will be an exception thrown at runtime trying to execute the first invoke exact. Okay, let's try to do generic invoke. Well, it works, but from compiler perspective, not that well, because inlining doesn't work. There is when you do an invoke generic right now, there is a cache on a method handle which tries to cache the result of the latest S-type adaptation and reuse it. And JIT can't see through that and just issues a virtual call. Well, it's not what we need, right? We want a really packed vectorized code. Okay, let's adapt method handle beforehand and invoke. And we get boxing on every invocation, both when we pass something into method handle and getting the result back. So the method handle we invoke is, well, it accepts, it expects value types. It works on value types. The problem is that the tooling support is not there, and that's a deliberate decision with minimal value types. So all the usages, use sites, call sites will work on objects on L types. So we have A loads, A stores, and invoke virtual is on L types. So what kind of alternatives do we have? Either generate Q-type bytecode or compose method handles. How does it work? How does it look like? Okay, let's see what can we achieve with bytecode generation. Maurizio did an excellent job with a new bytecode library, which I'll use here. So it supports Q types. That's the first library which supports Q types. I hope Remy will come up with the MVT support in ASM, and it will be possible to write Q-type bytecode using ASMs as well. But unfortunately, we are not there yet, and the bytecode library, which Maurizio wrote, is the only way to issue bytecodes, Q-type bytecodes right now. There was a workshop on bytecode generation yesterday, so that's about that, but the library Maurizio told you. So we need to use, so there is no way, there is no support on bytecode level for the operations we need, so we have to reuse method handles. So we take a method handle we got from the factory. Here I embed it as a constant pull patch. We have that support. And then load arguments and invoke. And I have here Q types, so no boxing. And the method handle I use is also Q typed. So it has derived value types in the signature. First load, second load, the same, okay. Sum, again, Q-typed bytecodes and the Q types in the signatures, and store it back. Everything happens on Q types, no boxing needed. Great. So what about method handles? How can we express the same functionality using method handles? Okay, it's a bit more complex, unless you are afraid of bytecodes. So we have method handles, primitive operations. We need to compose them. Okay, collect arguments once, collect arguments twice, collect arguments again. It looks similar to what we need, right? Two loads, add, store, but there are too many arguments. We need only 4, right? 3 arrays and an index. Okay, we need 2 permute arguments to avoid some duplication, and here we are, right? We have a method handle which implements what we need. Okay, how it relates to Q-type bytecodes. We have method handles which are on derived value types, but hey, we need Q types. JIT compilers speak bytecodes, right? So where are Q types? They are on Lambda forms. So Lambda forms were extended with the Q types. So on Lambda form level, that method handle looks like that. So the method handles are stored on method handle instance, and the bytecodes operate on them. So on bytecode level, we see Q types again, but since lambda forms are erased, instead of concrete value type, we see underscore underscore value. So that's what Frederick mentioned when talking about JIT compiler support. That particular code shape causes problems to JIT compiler, so additional support is needed on compiler side to be able to find out what are the concrete value types there. But C2 works fine with that, so it's able to eliminate buffering in this particular case and get decent code generated. And how to use loop body we created? Well, here we can iterate over the array and invoke the loop body on every index with a stride of a vector length. We can do that here because the type of method handle doesn't have any Q types. So it's expressed in terms of primitives or objects. All the value types are hidden inside. So here you see all the value types are inside. Nothing returned or no value types are passed in. So we can safely invoke the method handle and get the decent code. So we saw two approaches, bytecode generation and method handles. Well, do you like that? When I heard, so Vincent on Monday coined a new term, and I liked it so much because it was so close to what I have been feeling working with the method handles in MVT. So it's too painful. Even for that simple example, we just load two vectors, do a single operation, and store them. We have to do multiple steps to get desired result. But we think we have a better story for working with vectors. And here is Jan again.
All right, pass it off. Yeah, so the introduction of MVT and value types gave us a really good story to map stuff from the code snippet level to something we can use to generate reasonably efficient, pretty nice, tight code. But the path there is, like he said, somewhat fraught. You can do it. It just takes some doing, and one might imagine that everybody who engages in this is going to end up with a giant harness that they end up writing to make their lives easier. I mean, we didn't have any examples with method handle-based looping or anything in these slides, just because it would take more than 2 or 3. But we do have some solutions running. It generates great code. So at the very least, we're to this point now. We're up to method handles. You can use method handles with Q types, value types, or minimal value types, and code snippets. So at the very least, we have this functioning mid-range step, sort of in line with how MVT is on a path towards full value types. We now have a partial pathway to vectorization. So one thing that occurred to us is that really there's no better way to talk about expressions than to just talk about expressions. So the original spec for the vector API had a number of higher order components, and those were primarily intended for you to talk about vectors in lane-wise fashion. So, traditional A plus B times C type situation. It's natural, and it seems like it should just be liftable to the vector space. So we've been doing some work on that with higher order vectors. these are some of the examples. And you can, we talked about this last year, but we'll just reiterate it again. If you see this is a really natural thing to want to do to vectors, is to lift a unary operator or a binary operator over the element type to the vector. But even in this abstraction, you've got a couple of issues. The parameterized type is boxed, and you're going to be expressing things in terms of scalar types. So how do you convert your scalar types to vector types? You're basically walking back to auto-vectorization again. So what do we do? What does one do? So given some lambdas, like what are some of the options? So one of them is cracking serializable lambdas, getting the bytecodes, walking the bytecodes, applying abstract interpretation to the bytecodes, and reproducing an expression tree, and there's your expression again. Basically what we want is to get to the expression. How do we get to the expression? Higher order functions deliver us the expression in some packed form. How do we get it back out again? So bytecode's one way, but you can still introduce, the programmer can still introduce, a Turing machine and a lambda, and what are you supposed to do with that? We want a more predictable path to performance. So regular lambdas are a bit too expressive, so they're not the greatest mapping. So what about reinterpretable higher order functions? How about, what if we were to take something like an expression like so, and just, consider it like it's a tree. Given some tree, we can take that tree, we can traverse the tree with some kind of vector ops collection, maps to operations to method handles of a particular width, scalar forms, or vector forms, and we can produce scalar kernels and vector kernels that are isomorphic to the same expression. So with that, you can then populate your pre and post loops, kernels, and your vector loops as well. That's cool. So how does one do that? One way that we have been experimenting with it is to get to the expression tree by cheating, which is to just say, hey, programmer, make the expression tree yourself. Don't write like a traditional scalar expression, but use a little library, construct the tree, and we'll traverse the tree that you construct. So using a builder, the developer can construct a tree, and then the libraries can traverse it. This is a really common thing in functional programming. You come up with an ADT or something interprets your ADT, and then and dispatches based on that. Scala and Clojure, ML, Haskell, that's just like second nature to those languages. But in Java, it's not exactly the most natural thing necessarily to impose on programmers. Let's see, so this is an example of a little mock-up we did and threw it up it's in Panama, the Panama repo right now, links at the end or on the slides when you get them. But we hide our expression trees inside of a lambda, and then bind parameters explicitly, and then hand this off to an ops builder, which then populates the expression tree with leaf nodes, and then visits all the nodes and reconstructs method handle-based equivalent. So this is a way you can walk an expression tree with your pile of method handles and reconstitute a kernel that way without having to do it by hand. Oh, and I should say that in Vladimir's examples, I think it's unfortunate, but one of the first things you want to do when you write kernels is to write expressions. And when you do method handle combinators on expressions that are in operations deep, that's when you end up with these massive fan-outs. And then you have to do permutes, and sometimes you have to shuffle indices around. So just focusing on expressions and a nice way to kind of encapsulate that prevents a lot of the pain gramming that's associated with wrangling permutes. And so just building on top of that, we can say, okay, well, say you have a reduction like a left fold or a reduce. So we can use a builder that's pre-specified to that. You give an expression tree of that shape with an accumulator and a node, and then it can do reductions based on some expression you build that way. This boils down to, this decomposes into, or recomposes into method handles with loop combinators, which I believe loop is JDK 9, isn't it?
Yes.
Yes, so cool. And this is another one with masking operations, ternary-style mask operations, and these examples all fall out pretty well with the expression tree approach. But it's something that we're still working on and can be improved upon, and we're seeking feedback for these types of things. So expression trees are basically a front end. Right now they live on top of method handles with code snippets, but we could reorient them to face the vector API through a method handles interfacing, or just look at bytecode spinning as well. But in the end, the ultimate goal is something that looks more like this, where we're not concerned as much about size. We can talk about parameters in lowercase form. We can act as, we can look at our data sources and array as more of a view style, and then we can just throw in our lambdas to manipulate those. So our project status. Okay, I think there's one detail I didn't stick in these slides, which was yesterday, and this is something that came up yesterday when John was talking at the workshop. John mentioned what he called liftable lambdas, and I just wanted to dovetail on that what this is with expression trees is essentially I want to say kind of a workaround that does lifting, a kind of lifting on its own, but this could be superseded by an infrastructure for generalized liftings from lambdas or higher order functions in Java. So if you could, symbolize a lambda body in a particular way and then reinterpret that, and that was a thing that was available to everybody to write their own custom liftings, then the expression tree approach and the reinterpretation of lambdas could live on top of that work as just a use case of generalized liftings in Java, liftable lambdas.
So here in this example, we have a lambda. Mm-hmm. So that's the most natural way to write expression trees in type-safe manner. So, but we are not there yet, and we don't have crackable lambdas, which are required to reliably vectorize and predictably vectorize such code shapes. So that's something for future work.
Mm-hmm. Yeah, a rising tide lifts all boats, and the vector API is definitely riding on the MVT wave, and ultimately the value types wave will improve the experience for users of the vector API.
So minimal value type based vector API is a first step in the right direction, and once there are more support in different areas, we can piggyback on that work to mm-hmm. provide more fluent vector API, more natural for Java programmers. But unfortunately, we are not there yet, but we are moving in that direction.
All right. So now back to project status. MVT-based vector support in the JVM, we've talked about. We have, we're very prone to going down rabbit holes when we discover interesting things. So one thing we've been working on at Intel is enhanced intrinsification for the vector API. Since it's so specified, so well defined, the number of classes, the concrete instances are fixed. It's essentially a closed world. We've been experimenting, Razvan, one of my coworkers at Intel, has been experimenting with specializing and intrinsifying based on the type hierarchy of the vector API. And he's gotten some pretty good results. I think that's on a late slide. Yeah, just last tidbits. Vector API, the latest vector API specification, we had a big post a couple weeks ago, and then Paul Sandos, the master of APIs, got in there and cleaned up my mess. It wasn't a mess, but it needed cleaning, and he knows how to do it better than I do. So it's in pretty good shape, and it's also susceptible to targeting or enhanced intrinsification. So the intrinsification patches that I think are inbound to Panama that demonstrate that work on the spec API as it exists now. And then the expression language is in there, and it's all in Panama. Yes, I got ahead of myself. I do that every time. We've been experimenting with all this stuff in C2, playing with C2IR. And so we have that workload from a similar workload to before. You thread in a spec vector. You fill in a templated whole-based style programming. We're doing masks. This is sort of a contrived example. But the generated code is on the right, and you can see it makes proper use of blends and adds and its loads and stores. And it's pretty tight code, and it leverages a lot of the existing C2 architecture.
So this particular example demonstrates that intrinsic-based approach is on par with machine code snippets, which are used in Panama. So we don't need to bring machine code snippets along with the vector API. We can untangle them. And since right now we try to migrate to Valhalla project to build something on top of minimal value types, so we chose the direction from Panama to Valhalla and not the other direction. So this it's much easier to port intrinsic-based approach, and this particular case demonstrates that the approach itself is on par with machine code snippets. We can achieve the same result with a simpler solution.
Mm-hmm. All right, so these are the contributors. That's us and some other people. And then the materials, so references, and then once again the safe harbor statement.
So yeah, we are done. Thank you.